You said 2 per week. It's good. But when?
But this should be a sprint to the finish. We're not finished yet.
Yeah, this it's not finished yet.
You know what, guys? After you're done, we can connect it to the calibration station and see how it works. It's like almost really good. All the way instead of now.
Yeah.
Let's see how much it is processed.
But on Thursdays, usually TVs at Dilson. Wednesdays for.
This is variable. I can decide. But usually it goes.
When are we going to Maxim's?
I got it used to Thursdays because Maxime. Okay, I got this used to Thursdays because I used to have classes. But I can move that.
I got used to.
No, I don't care. It's good to have the sprints on due day, so we don't miss them. We don't
Well, I think a sprint on the meeting day is good.
Okay.
Because if we start at 9 a.m. sprint till 4, then we can have results, discuss, and then regroup for the next sprint. What do you think, TP?
Yeah.
Because that way we can record and transmit all our successes and problems. The Sensorica committee to.
Thanks a lot.
Ooh.
Yeah, makes sense.
So for this sensor, the next sprint will be when? For this sensor, this week you continue this sprint, this current sprint.
This sprint is we almost reached the finish line. We were so close.
Well, not the finish line because I still need to do some alignment.
Now we're at the optical stage. So
Yeah.
we got there almost, now we're just going to fine tune it.
Actually, I have a lot of notes for today's thing.
We actually almost reached sensitivity of our old mosquito with all the problems. And now we're just at the beginning of this. Heading it off.
Like putting it together physically by hand.
Yeah, we tape and spit and glue it. Like, and there's like a blue tack holding the LED in and all this other crap. We actually have to go.
Nice, man. Very nice. So, when you optimize this will become
But yeah, but read the problems that I put in there. There are some issues.
Okay, so I will send you a reminder to coordinate for sprints.
I have a question. Those issues that you have, they are, how to say, they are physical, so the issue of principle, or they can be solved by finding the proper parts. So basically, if you find proper parts that match.
Yeah, we can put money on this problem, or we can do more people last year.
Yeah, exactly. That's what. Yeah, exactly. So basically, it's either you order something that will match what you pay for it, or you do it on your own.
Yeah. But what we're doing now is we're proving the principle.
But then, there, like the principle speaking, there are no more issues.
And also, I have to emphasize that this is with the PBT results.
Today?
This, yeah, everything we're doing today is with the PBT.
So
There's no mosquito, there's no electronics.
the Austrian one?
Yeah, this is no electronics.
Okay, so basically,
It's a LED to smart thing to acquisition card, nothing else.
is it how it will be? Or
I hope so. I don't ever think of a surgeon for this mosquito again. We still have it.
Well, unless it's if it's something like a fuse, you want to put some.
Like I still have this year our ideal setup with the cooling and everything. That's gonna be when we have our. Because we're not at that stage.
But the one that it's very simple and nice.
Let me.
But do you want to put something like a fuse or something like some mechanism saying it's like?
Oh yeah. Protection.
Yeah.
You know, I'll think about that. We have to eliminate any path of electricity from humans. Yes, it can be isolated entirely.
So we would have more noise without the TV, right? How do you run the TV? Do you amplify?
No, I could not. Minus 12 volts, plus minus 12 volts. Now you have a clean 12 volts. We have 15 millivolts. Beautiful. Do we have batteries on there? ideal power sources, we're going to improve it 10 times already. Or double.
We do try with the mosquito because that's a little bit cheating because we need to compare this new technology with LED with the mosquito.
Yeah.
To see if this sequence.
I never got that photo that has to work. Okay, 50 photo that. Never worked with mosquito.
What?
I don't know. The mystery.
Okay.
Okay, can you take the lead, TB, on Philip's project and our system for organic space agency? We measure signal through a Y junction coupler splitter coming from the first transducer.
Well, okay, so we had the architecture of the mosquito, basically, meaning that we have a Y coupler splitter and we had a transducer. And we see no Fabry Perot and we see a very stable signal.
So these are the results of today?
Yeah.
Oh, okay.
Yeah, I just put them in instead of talking, they're in. There are some problems. So if we work with LEDs, the problem is to miniaturize the fibers because it's very hard to couple the fibers, as we can see. I'm sure we can improve a lot. And now I'm placing a new lens in front of the fiber. That's going to improve maybe a few times the signal. But we're using so much light now. We just use brute force. We use so much light that the LED is getting hot.
Okay. Did you write it somewhere, or?
Yeah, I wrote that we are just blasting fiber. So it seems to be very stable. If you want to go back to the laser, what's the optics? They suggested already a few things that can improve. And one conclusion is that the Chinese solution with an isolator in front of the laser was the Chinese solution was actually not working. So
insulator was not working.
yeah, it's already in the text. So that's why we went to the LEDs because the isolator, the Chinese isolator with the laser didn't work.
So what do we do with this insulator? We decide. Oh, we conclude it doesn't work.
Isolators don't work well with multi-mode fiber. That's the conclusion. If you go for single mode fiber, you can use the isolator.
Oh, well done.
Fibers, okay. So, okay. It's because of multimode.
Yeah. Yeah. So we tried, we had some ideas that maybe the noise was coming from the laser, from feedback. So we ordered the Chinese isolators, lasers with isolators. Thought that this is going to clean the noise. It didn't. Okay, so that's why we went with the LED. That's the logical steps, right?
Yes.
And the biggest challenge with the LED is to couple the LED into the fiber. I should mention that, Jonathan, he found some LEDs that have 4 wires on the semiconductor. So this gives you a beam with unobstructed beam, yes. So you have a beam that the center of the beam is clean, So the one that we tried, the normal LEDs, they have the gold wire right in the middle of the semiconductor, the emitting semiconductor.
Mm-hmm.
And the problem with that is that in the middle of the beam, you have a dark spot.
Yeah, blind spot.
And a blind spot, and it's hard to couple it in the fiber, because the fiber is centered to the center of the beam, right?
Yes.
Okay, unless you have some optics and you work on far field, in far field.
So did you overcome this problem?
Yeah, with this one, yeah. So yeah, we got some signal, yeah.
How did you overcome the coupling?
The coupling, well, the
blind spot.
Well, the blind spot, we use a fiber with extra
we use a
4 wire bonds.
we use a different LED that doesn't have something in the middle of the thing. It has 4 wires on 4 corners.
Okay, you already had this LED.
Yeah, we ordered it yesterday.
Oh, okay, it's this one that came today.
Yeah.
All these results are from the stuff we ordered today. Yeah, that should.
Wow, it's a real sprint.
This is an 850 nanometers.
Okay, so anyway, we will have a report about this sprint.
Yeah.
So maybe you can go to the next topic. Ivan, literature review and system design are in progress.
Yeah, there is one more thing. Daniel right now is working on the positioner for the electrodes for the bath that we already have, the one that we use for chemical activation, and the one that he is planning to 3D print. So basically, with this positioner for electrodes, we will be able to activate samples with the new bath. And I would say we can try and do experiments here.
Here?
So, yeah. So we have the frame for this bat that we can put on the table, put the bat on the frame, put the microscope on top, and try to do experiments right here.
With frozen?
With alive samples or, well, with both types of activation. So with that, we can kind of expand our experimental, you know.
You can catch a dog in the dog park here.
Yeah, we can catch anybody. Anyway, so that was just the add-on. Regarding the our project for CSA, I'm doing now the literature review, and according to this review, there are two types of scaffolds that people are using right now. It's a simple scaffolds and ill-defined scaffolds, like complex ones. So simple ones, they can be either synthetic or naturally made, like of natural polymers. For ill-defined scaffolds, people use different, very complex types of media, like matrigel or reconstructed tissues.
Mm-hmm.
So according to the reviews, the most optimal solution is simple scaffolds made of naturally derived polymers, like chitosan, for example, or collagen. Okay, so this seems to be our option for making scaffolds for cell culturing, muscle cell cultures. So basically, that's what people use for tissue engineering.
Collagen?
Collagen or chitosan.
Okay.
So I need to talk to Philippe and ask him if he knows someone who works with these type of scaffolds for tissue engineering. He told us that he knows someone who has expertise in this. These people, they will be able to give us some advice, and maybe even we can pull them in like as collaborators. Because I mean, I would love to learn these techniques, and that's what we eventually will need to do. But for now, we are very limited in time. So
yes,
maybe if these people are in Montreal, that would be fantastic, because I could probably Phil can arrange this, and I could go there and see how they work with the scaffolds. Because I used to work with the cell cultures before, but it was 2D. It was on the like single layer of cells on the Petri dish. So I never worked with the 3D tissue engineering. And I also learned something very interesting from these papers. Like the size, it gives me approximately the idea of the size of the future setup, because the scaffold must not be too big, otherwise we can have the necrotic sites inside the scaffold. So we can grow up to a few cells, like a few mature myocytes within one scaffold. And
a few cells? How many?
Well, I don't know how many cells, but I know approximately how big the scaffold must be.
Oh yeah? Okay.
Yeah, and we can make molds to make these scaffolds, basically, of a certain size and shape we want. But here is another interesting thing, that in order to grow these cells, we need to train them.
Train?
So, exactly, yeah. So we need to apply mechanical deformations on the scaffold.
To train the cells?
Yeah, in order to make them mature, you know, so they grow and
Oh yeah?
differentiate better. There are articles about that, how to apply mechanical deformations on the scaffold. So the cells, they grow and they become more like real cells in the muscle, because people use these cells to implant into damaged muscles, for example. For you know, when working with different myopathies or traumas, or even for plastic surgery. So we will need to have a single axis piezo very well working. Jonathan?
Yes. According to Frederick's progress, we'll have one soon.
So did you listen to? Were you listening to what they were
Yeah.
saying? So in order to grow cells within the scaffold for 3D,
Yeah.
people use motors to apply mechanical deformations on the scaffold, and also activation. So when we build the path with electrodes, so there are two ways to train the cells while they're growing.
Right.
So basically, that's how it will be. Like the path where we put the scaffold and we see those cells on the scaffold, it will be the growing, basically, space for these cells. So we will incubate those cells right in the bath.
Right.
With the pre-attached scaffold. And the scaffold from the very beginning will be attached to the transducer on one end and to a rigid lever on that end. And this rigid lever will be connected to the motor,
Yes.
piezo motor.
Right.
Yeah. So that's what we will.
What's the frequency of the motor?
That I don't know yet, because those papers that explain how to train those cells, I kind of don't have access to them. So I will need Philippe to do that.
And the movement they move is micrometers or?
Micrometers. Well, it depends on the size of the scaffold. So for us, it will be tens of micrometers.
Because some of these use a piezo speaker.
Yeah.
We
Well,
just put a signal in. Those are very low voltage. It's any signal generator can do it.
so right now I'm working on the design of the bath for these needs. And when I figure out, after I talk to the experts in the tissue engineering,
Right.
I will figure out the size of everything. And then we will see how many micrometers, like what would be the distance to move transistors. So basically for now that's it. So I'm designing the bath. Actually there was one more thing that we will need to modify the mosquito and actually simplify it. So the mosquito will look basically like the connector without the spring block.
Okay.
So I removed the spring block, and we will get rid of the glass tube as well. So it will be this sensitized fiber sticking out right from the metal part,
Okay.
and we will put a bit of epoxy so it's fixed.
And is it a constriction transistor or
Yeah.
physically sensitive?
Constriction.
Either one, but the constriction probably is better because it's short. So I consider it to be 5 millimeters approximately.
And there's no light coming back, so you don't have to analyze.
Well, yeah.
What?
With constriction,
Yeah.
there's no light coming
Yeah,
back.
just
So.
like, we make assumptions after.
Anyway, so basically, that's what and the whole thing will be embedded in the body of the bath. So that's what I.
Click and click out.
Yeah, and the body of the bath will be fixed inside the device. So it's like the incubator and the cartridge to measure the thickness. You know, I think that it's a good concept in general because I see a lot of studies with different types of cells, not necessarily exciting. Like, for example, people work with osteocytes, it's like those cells that eventually become bones.
Yeah.
For example, applying different
So
stretches.
what we're doing is we're applying the actual movement to it, and we're seeing how it reacts.
Yeah. So you study either elastic properties, or if you activate, you can study active properties. If it's a muscle, for example.
So if we master this scaffold stuff, we can have the cells much more easy to handle. It's not a single cell you have to to tape you or to catch.
So yeah, exactly. Ideally, what it will be that bath with the scaffold that we put in, and then we see those cells on the scaffold. When they grow, we start to train them. They change the growth medium. They grow, differentiate, so they become mature myocytes, attached from the very beginning to the.
But couldn't we just use a piezo, like we move the piezo and read it with the piezo? Maybe a piezo sensor that's, can we, like, when we move, do the motor action, can that motor also be used as a sensor motor? And have one piece to do both jobs?
Guys, look at the signal, man. I moved
Or they do that.
Is that what they did? They move it with the same sensor?
Not the same, but only piezos.
Yeah, okay, now I'm wondering if we can have a single piece to both. One crystal is a measurement and moving device.
I don't know. Normally people don't do it.
No, I've never seen it before. I was wondering if it's possible.
Yeah, because you have a non-moving piezo, which is the force sensor,
Right.
and a moving piezo.
And is this displacement or force?
The problem is that you need to know how much force it gives you. So the piezo must move the rigid lever, which is not bendable. You know.
Right.
So it does not. It's like way too more rigid.
Okay. Yeah. I see.
And the transducer is flexible, so its displacement gives you the idea of the force. So.
And you have an elastic band between the two.
Yeah.
On a flexible transducer and rigid motor. So when I pull on this, will the transistor just move rather than the whole thing flexing?
Well, it will move depending on the elastic properties.
Right.
So because you can move this much, but the transducer moves only half of it. So then you need to, that it gives you an idea about how elastic.
And when I pull a transistor to its maximum, does it stop or does it break?
No, well, you cannot apply more than, say, 30% of the initial length. I mean, like the mechanical deformation must be reasonable.
Right.
It depends on, again, it depends on the length of the sample, the number of sarcomers inside. So you measure per sarcomer length, and there's a, it's like a, how to say, it's a correlation between the length and the force that it produces.
Right.
So our task for now is how to make scaffolds and how to grow cells on these scaffolds.
Yeah,
like basically,
how to collaborate with someone who knows that.
yeah, because for now it's the whole science itself. You know, tissue engineering. It's a big deal now, and they pushed a lot since 2000. 1999, 2000. You know, it's like it started to develop.
And I asked my mentor if there's a pharma application for that, because if we can have the cells in a tape sensor while in a matrix, the scaffold, it can be systematically measured, produced and measured in cassettes, like we want to do for the Canadian Space Agency. Maybe it's interesting for them to test tens.
It gives it's a very wide field because people, they use scaffolds to grow any types of cells. Like it's so much, like it's a very big thing itself. So having the device that can produce and train. So with this device, first of all, you help them to grow because you're training them and you apply different.
And you have to automate
loads,
this.
Yeah.
So if we do the job for the Canadian Space Agency, a cassette that has already the fluids that change.
That's how I see it. If they agree on that, so we supply them with not the device on, but with the scaffold with cells inside. So basically, they just give us the names of the cells they would like to test.
Right.
And we, in collaboration with Philippe and probably his colleagues, provide with the device plus the grow tissue inside.
And how long is that good for in the freezer?
It's not the freezer. It has to be alive.
So it has to live for years.
There are studies on that, how long you can sustain these cells alive, and it's pretty long. So it's definitely
months or years.
It's months. So it's but it's definitely enough for the space studies.
Right.
Yeah, it's very.
So and then for freezing and bringing it home.
So basically, the way I see it, like they, for example, they receive the whole bunch of these baths, like cartridges, with the grown cells inside, trained and everything. So they are ready to be exposed to zero gravity, for example.
Right.
they do all their tests, and then they take all these baths and send back to Earth for the protein studies. So on Earth, they retrieve those scaffolds, take the cells, and like destroy the cells and do Western blots, histochemistry, everything that does not require active, forcing, physiological studies. So,
and will these get damaged by freezing?
But they don't have to be frozen.
Okay, and like alive.
Yeah, they are alive. Well, after the physiological part is done, yeah, then after they can
freeze them.
Yeah, you can freeze the whole thing.
At -20 or -80?
-20.
Because -80 is a problem for the dragon.
Yeah, -20 is fine, but what like the way I see it is that we provide not the device only, but also the tissue side.
Okay. And the cartridge will have to make it like we send them this device and the cartridge to go with it, and the device stays there, and every mission they can send more cartridges.
Yeah, exactly. So
and then we sell the cartridges.
Oh yeah.
But the thing is that, like the way we can make the cartridge to make it convenient to work on the orbit. So it's sealed. There's no exposed liquid, no nothing.
Yeah.
But the same cartridge, simplified version of it, that is open and you can see what's inside and everything, can become a product for.
Can we? But do they even have to do anything with it? Or can they just take the cartridge, plug it in when they arrive, and then take it out when they leave? And do no work.
Well, ideally speaking, yeah, but
we can do that.
It's our goal.
If we make the system absolutely automatic, so they just push the button and it follows the protocol. So they have to upload the protocol. So for example, the set of cartridges comes with the USB stick, and they turn the program on, and it runs the experiment itself.
Right.
Good night. Okay.
Good.
We.
Very good.
That's it.
That's excellent.
Before talking about office stuff, maybe the Valnet, Bob.
Bob, hi Bob.
Can you hear us?
Can we hear it?
Yes. Yes, I
Okay.
can hear you. Sorry.
My speaker's on over there.
It's supposed to be. Hello, Bob.
Right.
I can't hear you a lot. Let me check something.
Hey Bob.
Can you hear me?
Okay.
Can you hear me?
Yeah. Go on, Bob.
Okay.
It's written Bob wants Jonathan to coordinate the bug feedback loop for the lab.
Well, I would like Jonathan to get involved in it. It seems, he offered to do so. I don't want everybody else to stop, but I'm not getting enough feedback. So I want more feedback.
Wait, 1 sec. Can you repeat? We can't hear you, so just wait, please.
You got a lot of feedback. Oh, can you hear me still? Or not? Yes? Can you hear me? Yes, you can hear me. Okay, I can't hear you. Somebody say something.
Écris-lui, François, dis-lui qu'on l'écoute.
There we go. Okay.
Okay, so now we can have a conversation.
Okay, so Jonathan.
Yes.
Okay, so yeah, I want you to step into the feedback loop. I don't want everybody else to stop, but yeah, I need more feedback. I'm not getting enough feedback, and it seems to me like you can figure out this stuff pretty well. So, and you said you had time to do it, so I want you to do it. And that's partly why I set up that test environment, so you can go just try stuff, see how it works, find out. Everybody else can do that too. All right, you understand?
So I'll break the sandbox before breaking the real system.
Yeah, yeah. Well, you know, if it breaks, it's the same code, it's the same data, right? It was as of this morning, you know. But yeah, try stuff, see how it works,
Okay.
break it.
And do I have access to the admin panel on there?
Yeah, all the same logins work over there. It's the same. It's the same data. Everything's the same. The only thing that's different is it's a toy database. So if you had a lot of people, you're on a real industrial strength database on the production version. The other one is a toy because it helps me work with it faster.
Okay.
But you know, so if you had a lot of people working on it at the same time, it would slow down the test version.
So you will have just a portion of the database, but you can have all you can.
No, it's all over there. The whole thing as of this morning. I took all your data over there from earlier this morning.
Okay, so we can put everything that we have in the system that we use. We can put it over there too.
Absolutely, and I can take it over there again. Right now, though, I just wanted to put someplace where people can try stuff. And Lynn's going to use it too because she's down in Chicago. She doesn't have her Linux machine there. So it's and plus I like to have a test. You know, it's good to have a test environment where we can try stuff and we can test things out before I put them in production. You know, on an internet server. Because sometimes it's a little bit different working on my computer than it is on